Okay, so today we're going to go over most of the linear systems. We'll do a little bit of Fourier transforms at the end, and as I mentioned before we started recording, this will be fairly interactive, so feel free to stop me if you have questions. So the basic idea that we're building up to is for all the medical imaging systems, one of the most important things is to characterize what's called the impulse response, which is basically like the response of your system to like a tiny object. Okay, so in this case, we have two little dots here, and each of them gives you a blurred dot. Okay, so that blurred dot is essentially the impulse response. And we're going to spend, and the basic idea is now if I give you two dots, if it's a linear system and also shift invariant, then I can get the output by just summing those two outputs from the individual dots together. Okay, so that's the main thing. And that process, if it's a linear shift invariant system, is called convolution. All right, so it's going to be a sort of complicated answer, but the picture is basically very simple, which means that for any input, we can think of it as a weighted sum of impulses, and therefore the output is just going to be a weighted sum of the response to those impulses. So that's the basic picture. Right, so if you have this basic picture in mind, then as we go through some of the math, it should make a little more sense. So as Dr. McVeigh talked about, one way you might measure an impulse response is you could put just like a little wire in, and this is an impulse response in x and y. And so then you could look at what's called the PSF, or the point spread function. All right? The way we denote the impulse is we call it the Dirac delta function after the physicist Paul Dirac. And in 1D, it's just delta of x. In 2D, it's delta xy, or sometimes people denote it with this thing. And in 3D, it's just xyz. And you can go to n dimensions. So here's the basic idea that we say we put an impulse into a system, and we measure the impulse response. And h of x is obviously a very common choice for the impulse response. But you can call it anything. You can call it g of x, y of x, whatever. But h of x is used quite a lot. So for example, if it's an X-ray system, that means if you have a point source, a point object, then the impulse response is just the X-ray image of that point object. All right? And so what we're looking at then is, let's say you put in an arbitrary function f of x, or maybe some arbitrary object. Okay? You know that the system response is h of x. That's the impulse response. So the question is, what is g of x equal to? And that's the question we want to answer, right? And it turns out the answer is g of x is equal to f of x convolved with h of x. All right? If it's a linear shift invariant system. So we're going to just go through that. For some of you, this is review, but it never hurts to review this stuff because some of it's hard to understand. All right. So even if you see the second or third or fourth time, each time you go through it, you understand a little more. Okay. Any questions up to now? Okay. So let's now talk about this y of x, this f of x here. We want to figure out how to represent that in terms of delta functions. Okay, because if I can represent that as a weighted sum of delta functions, then I know that I just have to look at the response of each delta function. Okay, and then I just sum up those responses. Right. So we're going to talk a little bit about signals and images. And so most of what we deal with today, with all our computers and iPhones, is discrete time signals. Okay, so when you look at your computer or your iPad or your iPhone, you're looking at a bunch of pixels. Okay. And so typically or if you're listening to an audio that's digitized, your MP3 is digitized, and so those are all numbers. So an audio signal would be like S of n. So for each point in time, there's a value, or for an image, you'd have S of mn. And so typically you use brackets to note discrete time signal. So this is a discrete time signal as a function of n, and this is a discrete time image here. Okay. And then what we're trying to do is we're trying to use these discrete time signals to represent continuous time, or sort of real objects. And so, for example, this might be, your true speech waveform. This is, what the brain looks like. And so those we argue that for for purposes of representation, they're continuous. So we assume time is continuous, or space is continuous in x, or x and y. Okay, and probably maybe 2 Fridays from now, when we talk about Fourier transforms, we'll also review sampling a little bit. Okay, because the whole idea is, we have these continuous objects, but obviously we need to come up with a discrete representation of those. So that process is sampling, all right, which we'll talk about 2 weeks from now to review. So the other delta function that's really useful to know is what's called the Kronecker delta function. And it's a really simple and nice function. It's defined as follows. Delta of n equals 1 when n equals 0 and 0 otherwise. So really nice function. And the nice thing you can do with it is, so this is what delta of n looks like. And then the important thing is to know what delta of n minus 2 looks like. So it's just a shifted version, right? So the delta of n is equal to 1 when its argument is 0. So this argument goes to 0 when n minus 2 equals 0 or n equals 2. Okay, so that's good to know. And so similarly for 2 dimensions, we can have delta of mn here. So that's just a dot at the center. We can have delta of n minus 2 of n. So this is shifted over by 2. Okay. And then we can have delta mn minus 2. That's shifted over by this by 2. And here we're shifted over in both directions by 2. Yes?
So is that a dot or is that like a box, like a pixel?
That is like a pixel because we're imagining it's discrete. So yeah, so right, it's just a pixel. Yeah, go. Oh, move that. Yes, sure, I can certainly do that. Okay, good. All right. Anything else? All right. So why is that important? Well, it means that if I have a function, like this is, say, my function g of n, and it's like a function 1, minus 1, and let's say 2, right? So I can write that as delta of n minus delta of n minus 1. Oh, actually, this is 1.5. And then plus 1.5 delta of n minus 2. Okay? So we start with discrete because it's easier to understand. Just saying any arbitrary function I write down, I can just write down as summation of shifted delta functions. Okay? So in 1D, it's just these are the coefficients and these are the shifted versions of the delta functions, right? So this would be g of k is like 1, and then it's minus 1, and it's 1.5, and the 1 multiplies when it's 0 shift, the minus 1 multiplies when it's shifted by 1, and the 1.5 multiplies when it's shifted by 2. All right, so that's the basic idea. So the equations are there just so you have them, but the main thing is to know that you can sort of express that as a sum of all these. Okay, so if you have that picture in mind, that's really all you need to know for signal expansion. All right, and this obviously you can do the same thing in 2D. And so an example of that is here's a 2D image. It's got A, B, C, and D. And obviously you can write that as a sum of 4 different images. One with A and all zeros, one with B and all zeros, one with C with all zeros, and one with D with all zeros. So once again, very simple picture, but very powerful. Okay. This is just writing it again. Now we've got C, D, A, and B. So now showing that we can factor out the C, right, and multiply. And this is obviously now a delta function here because it's 1 and 0 everywhere else. Okay, so this is now a weighted sum of shifted delta functions, right? So this is C times this delta function, D times this delta function, A times this delta function, B times its delta function. Okay, so when we write it down, it's just A times some delta function, B times a shifted delta function, C times a shifted delta function, D times a shifted delta function. Okay, but this is the basic picture to have in mind. Okay, so if you have that picture in mind, you can always remember what the equation should be like. Just a bunch of shifted functions. Yes?
So we're writing down B, C, and D with respect to A, right? Because A would be just like...
Well, this is, for example, this is A delta mn, right?
Oh, okay.
Yeah. So if this is the origin, let's say this is at the origin, then everything is shifted with respect to that. Yeah. Okay. And then this, for example, this would be B times delta m n minus 1 because the 1 is shifted over by 1. All right. So once again, yeah, that's a good question. And I think the nice thing about medical imaging is, there's images. So if you think about things in terms of what the images are and what's going on, then you can you don't have to remember the math. You can just sort of remember what's the picture of how things work. All right. So for example, if we were to do this one, let's just write out the few examples of this. So let's say this is G of Mn. This is the origin here. So this is 0, 0, right? So we know that's going to be equal to 7 times the delta function at the origin, right? Plus 8 times m and shifted by 1 over n minus 1, right? So we've got the 7, we've got the 8, and let's get the 5. Plus 5, it's shifted this way and this way, right? So it's delta m minus 1, n minus 1, and so on and so forth. Okay, so that's
M is for the y coordinate?
yeah. Sorry, this is m and n. Yeah.
Yeah, so that shouldn't be sorry, should it be like 8 times delta of m minus 1 coming in?
Oh yeah. So maybe yeah. So let's write that. Let's correct that. Let me see if I can correct that. So that's m minus 1 n, right? And then what is the other one? M minus, well, this one's all right because both of them, yeah, okay. So that's good. So yeah, there's always going to be, and even just so you know, this is something that happens all the time because MATLAB has different conventions, and anytime you're dealing with images, there's always going to be some like figuring out which is y and which is x, and then you get it wrong and then you just switch it. Okay. Obviously on a test, check it, but in real life, it's like, oh, obviously this is wrong. Although strikingly, even in real life, there's radiologists put images left, right, and neurologists put images right, left. So even there's like no disagreement on how you should display an image. So you have to always be careful. Like, is the tumor on the right or the left? You really need to double check and make sure, because you don't want to go in and like take out. And it happens, right? Sometimes someone goes in for surgery and they take out the wrong kidney, right? It's true. Okay, it's no joke. Okay. So if you're ever having surgery, double check the images and make sure they take out the right thing. Okay. These things happen. So if you know a little bit about medical imaging, then you can sort of protect yourself. Okay. Dirac delta function is a very interesting function. We're not going to go into too much detail, but we'll talk about some of the properties that are useful to keep in mind. Basically, it's equal to 0 when x is not equal to 0. And the only other thing is its integral is 1. And that's all you know about it. Yes?
How is that different from the impulse function that we've just been talking about?
Great question. So the impulse response function, the delta of m is a discrete function. So it's only defined for integer values, like 0, 1, 2, 3.
Okay.
Right? Now we're talking about continuous values. So x can be anything from minus infinity to infinity. Okay, so it's like the in calculus, there's continuity and things like that. So it's a continuous. Well, it's not a continuous function, but it's a function defined on the real line, and therefore it's a really weird function because it's 0 everywhere except for 0, and it has an area of 1. So it can't really be a real function, right? Because it's basically not defined anywhere except for at one point. Okay.
So the impulse function, just like if you integrate impulse function, like it's only going to be
it's 1.
Area for that, right?
Yeah. So all you can say,
1, right?
The area is 1.
But you're saying that it doesn't exist at every real point.
It only exists. Well, all you can say is it's 0 everywhere except for 0.
For the impulse.
Yeah. So basically, what it looks like is here's x. So we draw it as an impulse response.
Okay.
So you can think of it as the impulses at 0.
Okay. And a direct delta function will look like that.
Yeah. This is the way the Dirac delta function looks like.
Oh, I'm sorry. I was asking for the impulse, just like
the
one that we were reading before.
Oh, the other one, the Kronecker delta.
Yeah.
Kronecker delta, the way you draw it is like this, because it's only defined at integer values. So you draw it with a little circle because for discrete time things, it's actually so the Kronecker function is well defined, right? It's very easy to define, right? This is Dirac is a little trickier to define, okay? So there's actually whole books written about this. It's something called Generalized Functions, and so, you can literally take a whole course on that, okay? So we're not going to do that. But what's useful to keep in mind is, one way you can think of a Dirac delta function is essentially something that has width of 1 over tau and height of tau, right? So the area is equal to tau times 1 over tau equals 1, right? And so you just think of this little rectangle getting narrower and narrower and higher. That's sort of, in the limit, that's the Dirac delta function, okay? So that's all we're talking about. Question?
Is that where you get into kind of the resolution of how wide 1 over tau becomes? Or is it just, that's just theoretical?
Right now, this is just theoretical. So basically, in the limit, so we take the limit as tau goes to 0. Okay. Later on, we'll talk about resolution. Yeah. So similarly, there's also the two-dimensional Dirac delta function, which is also it's 0 everywhere except for the origin, and it also has a two-dimensional integral of 1. So you can imagine it as one of these cubes that's getting narrower and narrower and taller, but the area underneath that cube is 1. Okay, so that's all that means. So this is just useful to know, and the other thing to useful to know is that it is a separable function. Delta x and y is written as delta x times delta y. Okay, so it's separable. All right. So Dirac delta functions aren't ordinary functions, but they are really useful. And the most useful property of the Dirac delta function is what's called the shifting property. And that just means if I take any function, a smooth function g of x, and I multiply it by, say, a shifted Dirac delta function, then that picks out the value of my function where the Dirac delta function is active. Okay? So this is a delta x minus x naught only has some value at x naught. So it's basically, it's like it just goes and picks out the value of the function. Okay? So this is one of the most sort of key properties of the delta function. Okay? And so this is why we'll use it for sampling. Sure. If I take, so for example, imagine this is a g of x is a smooth function, right? And let's say I come and multiply it by a Dirac delta function. Okay? And then I integrate that multiplication. So I take g of x and I multiply it by a Dirac delta function. And then I integrate that. Okay? So that's only going to sort of, every word is going to be basically 0, right? This is all going to get zeroed out, right? Because the Dirac delta function has nothing. So the only place that the integral is going to have any contribution is right around where the Dirac is. And when I integrate it, because the Dirac has an area of 1, it just gives me my function back. So it's a way of sampling my function. Yes, question?
Can you only pick out the values at 0?
No, this is picking out the value at x sub 0, because the Dirac is at x sub 0. So the Dirac delta function looks like, so let's say this is 0, right? This Dirac delta function is delta x minus x 0. Because the Dirac has,
It's just shifted.
yeah, it's a shifted, yeah. So that's one of the most important, that is one thing that's important to remember through this course is we do a lot of things, we shift things all around a lot, okay? And so shifted Dirac delta functions are how we do that, which we'll show later today. Okay, so that is one thing to make sure you understand that, when I have a delta function like delta x minus x 0, that's just a shifted Dirac delta function. Okay, and in general, any function, you should just be very comfortable with shifting it around. Like if I have g of x, what's g of x minus x 0? That's just shifted this way. If I have g of x plus x 0, it's shifted the other way. Okay, so that's, just be comfortable with that. Okay, any other questions?
So this is a
Yeah.
trivial, but
Sure.
the g of x being a smooth function, what is the definition of smooth function?
It's smooth.
Is it like anything special?
Well, it basically, because if it's not smooth, like let's say it's discontinuous, then when you multiply by the Dirac, if it's not smooth where you multiply it by,
There's no value.
then there's, yeah, it gets tricky, right? Like if it's a delta function there and you're multiplying a delta function by a delta function, then things get weird.
Okay.
Yeah. Okay. So for all intents and purposes for this course, don't worry about it. Everything is smooth.
Okay.
Yeah.
Thank you.
Okay. All right. Okay. One useful fact, which we'll come back to this later, but just delta A of x acts as 1 over A delta x. So we'll come back to this later, but it will be useful. 2 weeks from now, we'll revisit this, but I'll just present it now since we're talking about delta functions. Okay, so the way we represent a 1D function then, the idea is if I have some smooth function g of x, I can actually just represent it as a summation of lots of delta functions. Okay, so the same way we sort of had a discrete signal and we could represent it as the summation of discrete Kronecker delta functions. Now the only difference is, so before we had like a summation of g sub m delta, of like n minus m, right? We had a discrete summation. Now we're going to have a integral because we're in continuous time. But you see this form is the same. Where we had g of m, now we have g of xi. Where we had delta n minus m, now we have delta x minus xi. And then we have this additional integration. Okay? But the idea is the same, that we're basically representing every function with as a sum of weighted delta functions. Okay? So in general, we'll use discrete time to sort of motivate things, and then you just assume that the math all works for continuous time, but we're not going to go into showing it in this class. All right. Same thing with a 2D function. Now you have a double integral, you have the g of xi n, and then these are the shifted Dirac delta functions here. Okay, so you can imagine this is, if I drew little Dirac delta functions, any function could be represented as a bunch of little Diracs, each with a different weight. All right? Okay. So now let's put things together and talk about the impulse response, and we'll talk about linear systems, and then we'll look at some of the homework problems. Okay? So as we talked about before, if I have an impulse at xi eta here, then in general, I'm going to have some impulse response which depends on the input coordinates, but it could also depend on the output coordinates. Okay? So what that means is, what that means is the response to, like if I have a dot here, so one example of that is your eye, right? So here, if I have a dot out here, I see a dot, right? Let's say this is a dot, right? And over this range, it doesn't really matter where the dot is, right? So I could just have one function for the impulse response. But if the dot is out here in my periphery, then it's much blurrier for me, okay? So that's just arguing why the impulse response might depend on the relationship between the input and the output coordinates, okay? Now, when it doesn't depend on that, then we have a shift invariant system, and things are much easier, and so that's what we like to deal with. But in general, most things in life are not shift invariant, okay? So your eye is a perfect example. As you go off the center, the vision becomes worse, and that's why you move your eyes, right? Because you're always trying to keep things. So to your conscious brain, everything is shift invariant, right? But really, it's not. You're always adjusting to get it into that shift invariant part of your eye, right? Okay, so the first thing, so we're going to talk about linearity. Linearity has two components. The first, and you've probably seen this already in linear algebra, but it's one of these concepts that never hurts to review. So the thing is, linearity is as follows. There's first property is the addition property. So if I come in with some image I of xy, I put it into my system, I get out some image ky, k1, okay? And I come in with another image I sub 2, and I put it into my system, and I get out something k sub 2, okay? If this system satisfies linearity, if I come in with I1 plus I sub 2, I better come out with k1 plus k sub 2 for it to be a linear system, okay? So the response to a sum should be the sum of the responses. That's all we're talking about, okay? Scaling means this. If I come in with I sub 1 and I get out k sub 1, if I multiply this guy by a sub 1, right, so now that I have a sub 1 times I sub 1, my output had better be k sub 1, a sub 1 times k sub 1. Okay? So that means if I scale the input, the output should be similarly scaled. So that's the only two things you need for linearity. All right? So this is all it means. So for two inputs, for example, if I have I sub 1 and I sub 2, and they have outputs k sub 1 and k sub 2, now I put in my input is this. It's a sub 1 times I sub 1 plus a sub 2 times I sub 2. Then if it's a linear system, my output would be a sub 1 k1 plus a2 k2. Okay, so that's all linearity is. Okay. So why don't we do a simple example before we talk about the homework. So we're not going to use, it's a small enough room so we don't need to use the poll everywhere. But go ahead and sort of introduce yourself to your neighbor if you don't already know them. And let's look at both of these things. And we'll take a few minutes for you to sort of discuss and come back. We'll regroup in a few minutes and we'll ask the question, are these linear systems? Okay? And if you finish that one, you can go to the next one, which you have in your notes. But we'll just focus on these two for now. Okay? So go ahead and feel free to discuss this with your neighbor, and we'll regroup soon.
This you're adding by
We're just adding them, and that should be linear. Other one,
it should be added because it has to satisfy both for it to be linear. Because if we say we have another
I would, yeah, I would say the same thing as the multiplication.
Something like this. I mean, you're not really adding. Yeah. So you just kind of with this one. This is a problem. This one is yeah, this is scale. With this, we're not adding another. Just add a number. Yeah. Because this is
just looking at the inputs and outputs and the output just
First one is to give like second is to neither is the confusion.
it's just G plus 1
like with B it
and then
says
like the times it's what
Yeah, but only with the outputs. But the output of GX by through that system is not
are you saying that like the That's what's confusing.
Just like y plus 0.
That's what we thought then.
Oh, it should be just like
That's what happened. This would be
X, y plus 0 multiplied by everything.
I was good about it before.
Okay, let's regroup. So I'm going to let's ask each group what they think about A. Do you guys think it's linear or not?
Yeah.
Yes, okay. No?
Linear.
Yes. No?
Oh, we don't think so.
Don't know, okay. Is linear. Okay, so basically half and half, okay? So it's a good thing we're engineers.
Can you just clarify?
Yes.
Go.
Oh, yeah,
No,
good.
yeah, I mean, so I think at first I thought that g of x is like I1 and 10 is I2, and then later we were talking about no, g of x is the only function and 10 is just what the function is doing, like what your r of x is doing. So I guess,
Yeah.
what does the picture show?
Well, it means I put in g, I get out g plus 10.
Okay, so the 10 is just like what the r is doing.
Yeah.
It's
Yeah.
what the system is doing.
Yeah, so this is the system, right? This is the system, right?
Okay.
Oh.
Okay.
And then this is... So does anyone want to change their votes? Should we re-vote?
Yeah, revote.
Okay.
Yeah.
Do you want to change your answer?
I don't think it is the summation.
Okay, so you're saying it's no?
It's not.
What do you guys? It's yes or no? It's yes or no?
Think about this.
Okay. No.
Sticking to our answer.
What was your answer?
No.
No. You guys?
We think it's no.
No. You guys? It's no or yes? You have to decide.
Yes.
Yes, it is linear. Okay, and you guys need to decide.
It is linear.
It is linear. Okay, great. Either way is fine, but it's better actually to think about a problem, and whether you're right or wrong doesn't matter, because then when you see the answer, either way, it helps you learn it. Okay? So let's look at this. So if I have g, it gives me g plus 10, right? So let's look at scaling. Let's say I put in 2g, right? If it's a linear system, what should I get out? I should get out 2g plus 10, which equals 2g plus 20, right? That's what it should give me. But what does it actually give me? If I put in 2g, what does it give me back?
2g plus
2g plus 10. So it's not, doesn't satisfy scaling. Okay? And it's also not going to satisfy addition, right? If I put g, let's say I put in h, it gives me h plus 10, right? So if I put in h plus g, I should get out, you know, if it's linear, should be g plus 10 plus h plus 10, right? But what it actually does is it gives me h plus g, gives me g plus h plus 10. Okay, so that's also not. So on both accounts, it's not a linear system. Okay, so the point of doing this is that if you just think about it in your brain, it probably won't work. So for the homeworks, you basically just have to write it down and just say, does it satisfy? You know, you can write it down. For example, if you want to. In this case, we did scaling and addition separately, but I could have done it all in one step. I could have said, you know, what is the response to A1H plus A2G, right? And that would also not have worked either. Okay. So for the homeworks, if you want to sort of do it all in one step, you know, if you have some input f, right, then you might say, well, you know, what is the response to, you know, w sub k of f or something like that. Okay.
So like basically, if you can, if whatever your like your input is and give your response, if you can bring that basically into the summation, it's basically linear then, right? So for like I think the book kind of teaches it where if it's like outside, like they'll have whatever your response function is doing, and then like, you have your input and then response, then you can just bring that into it. It's basically.
Yeah, in general, things that are only adding and subtracting inputs or adding and scaling inputs will be linear. But for the homeworks, I recommend you just, the homework problems are obviously going to be slightly tricky, right? As was this problem. But as you can see, even it doesn't take much to be tricky, right? Okay. So what we're trying to do is emphasize that to make sure you know how to implement the actual definitions. Okay. And then when you do this, then you know you can fool your friends later. Okay. All right. So how about B? Is this linear or not? So is it linear?
Yeah.
How about you guys? Yeah. You? Everyone think it's linear? Anyone think it's not linear? Okay. So let's see. So G. Whoops. Sorry about that. G gives me 10G. If I did 2G, it should give me 20G, and it does, right? And also if I took like G plus H, it would give me 10G plus H, which also is correct, right? Okay, so that's a linear system. Okay,
Question.
yes?
So now, are we supposed to evaluate the system by introducing another input as well, which is h, right? In order for us to see if it's a linear system. Right?
Well, so in terms of, yeah, I mean, you can think of it as just different summations of, it doesn't have to be necessarily, like for example, one way you can do it is, you know, h could just be equal to 2 times g, right? That's another function, right? So it's just more if you sum things up, yeah.
So you're saying that the last example is g plus h, that is your input?
Yeah.
G plus h. Okay.
Yeah, but h could have just been 2g, right? So it's sufficient to, like, if I have f, I just look at the response to w sub k of f, right? Because that's a weighted sum of inputs now, right? Okay, so that's one way to look at it. I mean, so there's two ways you can do these problems. One is, you know, what I would suggest doing is, for intuition, it's a little easier just to think about 2 inputs, right? But if you want to do it generally, then you can write a summation. But, you know, from the point of view of whether it's linear or nonlinear, for most problems, just writing as 2 inputs is sufficient. Yeah.
I'm a little bit confused about
Yeah.
the first one there.
Yes.
When you put g plus or h plus g should be g plus 10 and h plus 10.
Yes.
And then we say that it's only we just add a 10. But
Yeah.
why?
Why is this the case?
No, the first one.
Why is this the case?
Is that because like when I take them separately?
Yeah. So
okay.
g gives me g plus 10. H gives me h plus 10.
Okay.
So when I add them together, I should get the addition of the outputs. Okay? Okay. All right, any other questions? Okay. We're not going to give you as much time to do this one, but spend about 2 minutes thinking about this one. And feel free to discuss it too.
That's what my
So you have two GFX.
If I have two, and I do both of them need to be actually I still just move them right. Even like I don't add the moving one. The moving will be bigger.
No, you're adding this and this and this.
Yeah.
Yeah.
The question is if we want the electric thing.
let's say that's the last.
Yes, so yeah, there's more.
But I think kind of
Yeah, so
Yeah, there's a two.
I guess I meant maybe I meant apologize. Because I guess I don't know.
So like if you want to add in some this box, then that's gonna go up.
Yeah, I know.
Yeah, see, that's what.
Like the one that has now, in order to get to the corner,
I mean, it depends on the
up by one.
If you do it,
You only do one.
Yeah, if it's a different size.
Okay, let's regroup. I know discussion is still going, but we have things to cover. So let's start from the back. Linear or not linear? Linear? Okay. How about you guys? Not linear. Okay, you just came in, so don't worry about it.
I think we have a different answer.
Okay.
Don't know.
Don't know. Got it. Linear or not linear? Got it. Linear or not linear?
Maybe linear.
Maybe linear. Okay. Linear or not linear?
Maybe non-linear.
Maybe non-linear. Okay. Linear or not linear?
I don't think get it.
I don't think so.
Not linear. Okay. Linear or not linear?
I don't think so.
Don't think so.
Yeah, no. Wait.
Okay. It's a tough decision, right? Okay. It's linear. Okay, so let's see why it is linear. So if I have g of xy, right? This is saying it goes to g of x minus 1, y minus 1, right? So if I have 2g of xy, right, it's saying it's going to give me what? And that is 2 times the original output, right? Okay, so that's scaling works, right? So let's say I have another function h of xy, right? And it gives me h of x minus 1, y minus 1, right? So now let's say I come in with g of xy plus h of xy, okay? So what's the outcome going to be? It's going to just take that thing and just move it up by 1 and right by 1, right? So that can be written as g of x minus 1, y minus 1, plus h of x minus 1, y minus 1. So that satisfies addition as well. Because this was the output for the first one, and this is the output for the second one. Okay, so that's good to know because we do a lot of shifting around. And when you do imaging processing or anything to do with images, you're always moving things around. So if it wasn't linear, it'd be a big problem. Okay, so it's actually good that it is linear. And in fact, what we'll find out later is we can write gx minus 1, y minus 1. It just equals gxy convolved with delta x minus 1, y minus 1. Okay? And so shifting things around, we're going to see, can be written as a convolution with a shifted Dirac delta function. And convolution is linear, so that's good. All right?
Sorry, what was the second check mark?
So this was, before you came in, there's the scaling property, and then there's the additive property. And we're recording this, so you can always go back and check that. Yeah. Okay. Any questions on that? So I think these are really good examples for showing that if you just try to use your intuition, then it's hard. And I know one of my professors said, you shouldn't use your intuition if you don't have any. Okay. Right? It's true, right? There's a great book called Deep Survival. Has anyone read this book called Deep Survival? It's all about people who get into really bad trouble because they go into places where they think they know what they're doing, but they don't. Like there's one about these snowmobilers who are like, oh yeah, they're just snowmobiling somewhere in Alaska, I forget where. And then they go see this like huge mountain or something. It's like, yeah, let's go snowmobile that. And the next thing you know, they're dead because they don't understand how high it is and the gravity and the effects of snow and things like that. So with engineering, you got to do a lot of problems. And then you have to realize that oftentimes your intuition is wrong. And so that's where you need the math to back you up. Okay, so you want some intuition, but you also want some math because intuition is not going to guarantee you that a bridge is not going to fall down or a spaceship's not going to blow up. Okay, like if buildings were designed just based on intuition, we'd be in trouble. Okay. All right. Okay, so let's talk about a little bit about how to set up these problems. So this is similar to the problem we just did. There's an addition. So this system here adds two things together, and it also so we're going to talk about the linearity. We'll talk about shift variance later. So you would do the same thing. You would say, okay, what happens if I multiplied my input by something? What happens if I took two of these things and added them together? Would it satisfy scaling and addition? So my suggestion on this is write things down explicitly, just like we did for those example problems. Just verify, does it satisfy scaling? Verify, does it satisfy addition? Okay. If you just try to guess the answer, 50-50 chance you'll be wrong. Okay. And so therefore write it down. Similarly for these, you're asked to see if each of these systems is linear. And so the same thing goes. Now, this one is a little easy on the linearity because it's two functions multiplied by each other, right? So without knowing anything else, do you think that's linear or nonlinear? Linear? Okay. So is like x squared a linear function? No, it's nonlinear. So anytime you see two things like two f's multiplied by each other, check, but there your intuition is somewhat useful because x is linear, but x squared is not linear, right? So probably it's not linear, but you need to double check. Okay. This one is interesting. Here you can use some intuition. It's sort of an integral of something, right? And integration, is it linear or not linear? It depends, but what is it? What is integration at its very heart? It's summing things up. It's addition. So it's probably linear, but double check. Maybe it's nonlinear, but you have some intuition on these problems, but sometimes professors like to be tricky and yeah, go ahead.
Like if you do I understand the x and the x squared idea, but if you did the scaling and the linearity test, wouldn't the scaling just be 4 times the RHS is 4 times that, so it works?
Well, so here's the thing. Let's say I come in with f, right? Let's do the scaling part. We'll do that for you, okay? So let's do the f, and this is saying if I put in f, so I put in f of xy, right? Yeah. And I get out f of xy times f of x minus x naught y, right?
Yeah.
Okay, so now let's say I put in 2f xy, right? What is this going to give me out?
It's just gonna be 2 times. It should, right?
It should give me, but what does it actually give me out? It's going to give me 4, right, times all that stuff. But it should give me 2 times all that stuff, right?
Because it's 2 and 2.
Yeah. Because remember, like imagine it's like you're putting in the f, right? Now you're putting in 2f. All that function does is it takes your input and it takes one of them, f of x, so if I put in f of xy, the output is f of xy times f of x minus x naught y, right? So if I put in 2f, it takes my 2f xy and then takes my 2f of x minus x naught, and those 2 times 2 is 4, right? Yeah. Does that make sense?
Yeah, I missed something.
Yeah.
I don't know, I just forgot it. I keep not looking at it as a function, just looking at it as an algebraic.
Yeah, so it actually might be useful. See how I've written it out as arrows? That can help you actually just think about it. It's like, think about what's going, go back to, what is a function, right?
Right.
Input, output. It's really, it's useful, but people forget about it and get into lots of trouble, okay? But just go think, okay, I put in this, I get this out. Now I put in something else, I get something else out. It's an operation. Yeah, it's a linear operator. You're asking whether it's a linear operator or not. So an operator is just a function that takes another function, right, and gives you a function out. Okay? All right. Okay, so let's talk a little bit about superposition. So we talked about how any input can be written as a weighted sum of delta functions, right? So this is a weighted sum of shifted delta functions, all right? And we also said that we could sort of, if we had a delta function like this, a shifted delta function, we could define its impulse response, okay? So I'm going to just sketch out the proof, but then it's on the next page. So what we want to do is we want to figure out, well, what is my response of my linear function, my linear operator to my input, g of m? Okay, and now we're assuming that L is linear, so it satisfies addition and scaling properties. So with those two assumptions alone, we can get a long way, right? So the first thing we can do is we know that we can take the L inside the multiplication. So it's g of 0 times L of delta m plus g of 1 times L of delta m minus 1 plus g of 2 L of m delta minus 2. Okay? So that's basically, because it's linear, it satisfies scaling property. For each one of those multiplications, the response to the scaled version of the response is just a scaled version of the original response. Okay? So this is using scaling property. Okay? Now we use the addition property. We can say that, well, all of these things is, let's see, how are we going to use the linear? So how do we use the linearity property here? What did I write before? Okay. Let's look ahead to what I did before. Okay, that's that. Oh, okay, great. Oh, yeah, we don't use that. So basically, then each of these is g sub 0. So this is the response delta, h of m. Let's see. H of, let's see, m prime 0 plus g sub 1 h of m prime 1 plus g of 2 h of m prime 2. Okay? So basically we're just saying we can write, and this can be written in this summation form. So all we're saying with superposition is if this is linear system, then so this was actually going from here to here was actually using addition, right? Sorry, screwed that up. And then going from here to, I use both addition and scaling at the same time, unfortunately. Okay, so I basically said that the sum of the inputs the response to the sum of the inputs is actually the summation of the individual responses. And then so I did 2 steps at once. Okay. Sorry about that. So if we look here, maybe I did it better here. So here, in this case, I'd used addition. Okay. And then here I used scaling. So here at least I broke it up into 2. Okay. And then we just get the answer there. So the idea is for a linear system, it's the superposition principle, which is basically if I know the response to individual impulses, then I can just scale those and add those responses and get my overall response. Okay. Yes.
So we know that it's g of m, right?
Yeah.
So if g of 0, so that expression right there, g of 0 and then h of m prime 0. Why is it not h of 0?
Oh, you mean why is this not h of 0?
No, the one on top.
Oh, this one here?
Yes. So why is it not h of 0?
Oh, right. That's a good question. It's because we're defining h of m prime k like this. So basically, the idea is this is the response to a delta function at k, right?
Oh,
so this,
k is then the value.
yeah, k is this value here, right? And so this is saying the output coordinates are m prime because it just sort of like the I example. There's some input coordinates and there's some output coordinates. The next step we're going to take is do a simplification of that. Question?
What is the purpose or benefit of changing the notation of L of delta of m minus k to h of n prime, k?
Oh, okay. Why do we do this step here?
Yeah.
Okay. The purpose of that is because the way we characterize systems is we actually measure their impulse responses. So h is what we actually measure.
Okay.
So what we're saying is if I have a system and I just ping it with an impulse and measure its response, h, then no matter what you put into it, I can tell you the output.
Okay.
So that's why h is important. So the response to an impulse is very important. So there's 2 things that are important: the response of a system to impulses and the response of the system to sine waves. Those are the 2 most important ways we characterize systems.
Is it essentially a way of getting the notation back to using h from an L for like the linear system and the direct delta? Or?
It's basically saying that if I have a system L, like let's say I have a big black box, and you tell me, what does that black box do? If I give you h, I'm basically telling you what it does. Like I don't have to give you all the circuits. One way, like if I gave you a system, I could either give you all the circuitry and everything, and you could figure it out. Say, go figure it out. Or I could say, well, I actually measured it for you already. I put in an impulse and I measured the output, and that's sufficient now to know what that system does.
I guess my question is like in the summation and everything, why are you bringing it back to h instead of just keeping it like in the
Keeping as L?
Yeah, keeping it as L.
Because we want to, because the L, we're showing that, for example, oh, you mean this step here. Why do we do that step there? Because that's the only place we use that step, right? We introduce the h. It's simply because that's just convention. We have an h, right?
Okay.
I mean, we could go around saying L of delta, but
so is it
we
just
don't.
Kind of shorthand, essentially?
Yeah, it's basically, it's so important it deserves its own name. Okay? Yeah. And then in 2D and in continuous, it's the same idea that if I know the responses, the impulse responses, then for any arbitrary input g, I can get the output. And this is now just a sum of weighted impulse responses. Okay, so this is still a sum, right? But it's an integrand sum of weighted impulse responses. Okay, but we're not going to stop there because this is still sort of too messy for us. Okay, so what we want to do is introduce another thing called space or shift invariance. Okay, and what that means, it's sort of like what we're talking about with the example of the eye. But if I have a shift invariant system, it means that if let's say I have this impulse here, and this is its output of the system, okay? So in this case, you can see that my system sort of blurred my input, okay? Now let's say I moved the dot down here, so it's this dot here, okay? If this is a shift invariant system, then my output should just be a shifted version of my original output. Okay? So it's a very simple concept. It's basically, if I shift things in space, then the output should just be shifted in space as well. Okay? Or if I shift things in time, the output should be shifted in time. And it should be exactly the same. Okay? Now that's a big approximation. Most things in life aren't like that, but you know, they are similar enough like that. For example, if you have a bell, right, and you hit it today, and conditions, the temperature and everything is the same tomorrow, you hit it tomorrow, it's generally going to give you the same response. So that would be an approximation of a shift invariant system. Okay. So for example, here's a time, like in time, let's say this is time. So the first Dirac delta gives me this response. So this is the impulse response. So the first Dirac delta would give me this response. The second gives me this response. And the third gives me that response. And those responses are simply shifted versions of each other and also scaled versions. Okay, because this impulse had maybe value of 1, this had value of 2, this had value of 1. So this goes 1, 2, 1. Okay? So that's all we're talking about, shift invariant systems. All right? And the output is now a weighted sum of our shifted impulse responses. And now here the key is that every impulse response, it doesn't matter where the input was. Okay. So then with convolution,
I just have a quick question.
yes, go ahead.
Why is this operate, or like, why is the image blurry?
Oh, why is the image blurry?
Like, why is it just not the object itself? Like, why is it?
Okay. Is anyone here nearsighted? Okay. You're not nearsighted. Okay, so that's why you don't understand why things are blurry. So, like when you're nearsighted, you know, like things look blurry. So that's like your system is like, there's a dot here, and then it just looks blurry. Or you can think of like, if you have a camera and it's out of focus, that's another system, right? Which it's just, so most systems are blurry because to make things not blurry is very expensive. Okay, so for example, another example would be like your iPhone or your computer screen, right? The more voxels you have, right, the more things are sharp, right? And so things are less blurry, but that's more money. So that's the idea that yeah, go ahead.
I mean, I'm trying to understand why are we trying to use a system that is blurry? Is it handy if we have a noisy, like, you know, like, or if we have a signal that's noisy? Would this be helpful for us to make it less noisy, I guess?
Yeah, I mean, blurriness does help with noise, but here's the main answer is money, time and money, which are equivalent, right, to some extent. So when we talk, for example, about in CT, for example, you know, now it's very fast, but in the old days, it takes time to go around and collect all those projections. In MRI, it's even more. We have to take time to collect it. So what we'll find is, to get something very sharp takes a lot of data. And so, for example, if you're in a clinical setting, you may not have that time. You know, if someone has just been in a car accident and they have to lay there for an hour to get scanned, they may be dead, right, by the time you're done. And you're like, this is a beautiful image of you, but you're dead. So you would rather maybe spend 10 minutes to get a somewhat blurry image and realize, oh, they're missing, you know, they have a huge hemorrhage in their brain and get them out to surgery. So that's the trade-off. If you have all the time in the world, then, like, for example, you know, very high resolution images, like you might take you take a cadaver and you could scan it for like days. You get a beautiful high resolution image. But you can't do that with a human because they're moving, they're breathing, they have to go to the bathroom. So, you know, you're never going to get a super high resolution image, okay? Because it takes too much time. Yeah. Okay. Okay, so in the interest of time, so the only thing that's different with convolution is now we take this linear operator. The input is, when it's a shifted Dirac function, now the output is just a shifted version of the original impulse response. So that's the key to all these proofs. And I think I'm just going to walk through it instead of writing it out. So let's see here. So here we want our response to our input g of m, okay? And we write out g of m as a weighted sum of shifted Dirac Kronecker delta functions in this case, okay? The next step is just we apply addition, And that lets us write it as the sum of outputs. The next thing we do is we apply scaling, right? And that allows us to factor out the scaling term, right? And then the next thing we do is we apply shift invariance. And now each of these is simply the same h, but it's just shift. Okay? So at the end we have, these are the weights and these are the shifted functions. And so that's all convolution is. It's saying, if I know my h, right, then you give me any g and I will tell you what the output is. Okay?
So you have to.
Go ahead.
Can you do that last sentence?
Yeah. So let's say I give you h, right?
Yeah.
So you know h, right? And then somebody comes along and says, you know, that's great that you know the response to impulse response, but what I really have is some other function g. And can you tell me the output of the response of your system to g? And so you can say, yeah, I can just tell you, because all I have to do is I have to just take g, break it up into different delta functions, and then those are the coefficients g of k, and then I just multiply that by shifted versions of my h, and I can tell you what my output is. So that's all it is.
So we always have to shift and scale our h, right?
Yes, that's right. So basically convolution you can think of as shifting and scaling an impulse response.
And
Okay.
is that all like known? Like, do we know how much we have to scale it by? Would that be like?
Yeah, so those are the those are the g sub k values here.
Okay.
Was there a question? Okay. So this is convolution from the point of systems, you know, understanding things from a systems theory. Now convolution is just a mathematical operation, so you don't have to think of it that way. In fact, the forms of g and h are interchangeable from the math. The math doesn't care whether g is an impulse response or h is the impulse response. So it's sort of, it's commutative, essentially. Okay. Any questions? Okay. So the output is the weighted sum of shifted impulse responses. So that's the main thing. So that's what we've been working up towards. Okay.
I have a quick question.
Yes.
This is all 1D or 2D?
This is all 1D and discrete because it's easy to think about, and then you just assume it all applies to 2D and continuous.
But,
yeah.
Just like with what you write in the first, like
Yeah.
H, and so I understand how like the second. So you see the second line.
Yeah.
I understand like L equals H m prime minus K, but like why is it m prime comma K on the left? Like that kind of gives the idea that it's two-dimensional. It's not, right?
Oh, right. That's a good point. Yeah. So this is not 2D.
Okay. So it's.
Yeah, it's just a way of writing. Well, I mean, it's just.
So it probably is different because 2D is with the round brackets. Like,
Well, no, it could be a 2D function. I mean, it's sort of, yeah, it's a bad notation, but it's sort of.
It's not 2D.
It's not 2D. Yeah.
Thank you.
Go ahead.
So what is m prime again in this case?
Oh, m prime is just sort of. We carry it around simply because sometimes the output coordinates can be different, but from now on you can just forget about the prime and it'll just be m. So for all the problems we do, don't worry about the prime.
Okay.
Yeah. Okay. So yeah. So from now on you can assume m prime equals m. Okay.
What do you mean output coordinates? Are you going from like Cartesian to polar?
No, it's more just, so the simplest example is, you guys didn't really do magnification this year in X-rays, but X-rays magnify things, right? And so, but the idea is, if you're just taking out that magnification, then if, you know, a change here of 1 is a change here in 1. So it's easy to sort of adjust it. So it's sort of like, you know, when you take a picture, right? Like if I take a picture of this room, then my picture is like this, right? So there's been a scaling of my picture. So the output coordinates are like tiny compared to the input coordinates, right? But I could just scale it up and sort of say, well, you know, that's something I can figure out. And so for all intents and purposes, the input and the output coordinates.
But the scaling up is not part of the system, what the system does?
It is part of what the system does, but you can just...
That would be what H would be, right? Like the difference in...
Yeah, so in general, like for X-ray imaging, you have to take into account the scaling, but then that makes a shift invariant. So you just say, well, whatever image I get, I'll just scale it back, and then so you can get rid of that shift invariance pretty easily. So it's one of those things that, yeah, you have to take care of it, but in principle, it's an easy problem to fix. Yeah. Like if someone just scales something for you and doesn't lose information, then you can always scale it back down.
Right.
So that's not a big deal. So then in that case, the input and output coordinates can be the same. And so for the rest of the course, we'll just assume that you've done that, right? Like, you do that all the time. When you look at a brain, you don't think, oh, the brain's that small. You sort of, part of you realizes, I'm looking at a picture that's scaled down of an object, right? And so in that sense, it's, the input and output coordinates, you're sort of understanding that it's the same thing, okay? But strictly speaking, you need an M and an M prime. But in reality, your brain sort of said that, don't worry about that.
So all the M primes are the output coordinates.
Yes. Yeah. Okay. Okay. So let's spend the last 20 minutes getting you at least up to speed on a little bit about how to do the mechanics of convolution. And we're not going to get to Fourier transforms this time, but what we'll do is spend the last 5 minutes just giving you some things to think about for the homework problems at least. And then you can talk to Professor McVeigh or the TAs next week for the homework if you need more help. Okay. Was there a question back there? No? Okay. Okay. So in 2D, in continuous time, the summation is replaced by an integrand, and everything is now continuous time, and so we have to have this differential term. But it's the same thing. These are shifted impulse responses, right? And these are the weights. Okay, so it's exactly the same form. It's just as much easier to think about in summations than it is in integrands, all right? And the way we denote that is g of x is asterisk with h of x, okay? And an extremely useful fact is if I take any function g of x and convolve it with a shifted Dirac delta function, it just shifts my function. This is extremely, extremely useful, okay? So you want to just commit that to memory. Okay, so actually, let's do an example of that. So let's say this is my rect function. So this is rect of x. Okay. So I want to ask myself, now I'm convolving it with these two shifted Dirac delta functions. Okay, so let's write out let's do this together. So when I convolve it with this Dirac delta function, it's just going to shift it over by a quarter, right? Okay, so then it's going to give me this, right? Minus a quarter, 3/4, and the value is 1, and the center is at 1/4, right? Okay, so that's what happens when I convolve with that Dirac delta function. Okay, and then this is all linear, so convolution is linear. So then I can just think about what happens when I convolve with this one now. So this is going to shift my Dirac function over by minus 3/4. Okay, so then that's going to be here. It's going to start here and go like that. Okay, so minus 3/4 plus minus a half is what? Minus 5/2, minus 5, right? And that's 1. Okay, so that's what my function looks like.
And then you're shifting the first one.
Yeah, so that's this one. Yeah. Okay. So anytime you see a function convolve with shifted Dirac delta functions, then you know life is good and easy. Okay. Otherwise, you have to do work. All right. But this, you don't really need to do much work. But you might still screw up. Students have screwed up, so just make sure you get this, because this is like the part that's a freebie, right? If this is on an exam or homework, you should just nail this. Okay. And if you don't nail it, then it can make the rest of the problem much harder. Okay. So make sure the stuff that's easy, you nail that. We'll come back to this one. Let's do a 2D example of this. So now I have a 2D rect function. So that looks like this. Okay. And here what I'm arguing is I'm going to convolve this with now these 2D Dirac delta functions. Okay. And since we say it's just shifting, so this one here doesn't do any shifting, right? Because it's right at the origin, right? So if I would draw the picture, then I've got one thing that's right at the origin. Okay? This is shifted over by how much? What's the shift there? Minus a half, right? Because it's delta x plus a half. So it's this is 1/2. Okay? So that's going to shift things over by a half, right? So I'm going to have another function here, right? So where they overlap, they're going to sum up to give 2. Right? So this has a value of 1 everywhere. Okay? And where they don't overlap, it's 1 and 1. Okay? So that's how you would do convolution with Dirac delta functions. All right?
So why is it 2 asterisks just to say it's 2D?
Yeah, so this is sort of like, in fact, this notation should have been g of x, y, right?
Right, yeah.
Yeah.
And h of x, y.
Yeah.
Okay.
That's right. So that's a mistake.
And 2 asterisks is just...
Yeah, that's just 2D convolution, but you can be sloppy. If you have two 2D functions and you're convolving them, you can just write an asterisk because it sort of makes sense. Okay.
So the dimensions is what makes the number of asterisks go up?
Yeah, so if it's 2D, then you would want to have 2 asterisks, but you don't have to. If you have two 2D functions and you have an asterisk in between the two, it's sort of understood it's a 2D convolution. So you can be a little sloppy with that. Okay, question?
I don't know the x values of this last, or like the answer. Is it just -1 and half, I guess, on the other side? Or
Yeah, so this would go from, this goes to a half, right? This point here is 1/2, right? And this point here is what?
-1?
Yeah.
-1, right? Yeah. Yep. So yeah, I mean, so there is a lot of shifting around in these things. But now let's get back to, we'll spend a few minutes talking about sort of writing out. One of your homework problems has you actually evaluate a convolution, right? So the basic idea is you would, you basically, to do the convolution, you just take one of your functions and you can do what's called flip and shift, which is you just take the argument and have x minus xi, and then the other one is g of xi. So let's do an example of that, I think, from the homework. Okay, so here you have f of xy is equal to x plus y, right? So we'll just set this problem up for you. And h of xy is equal to exp minus x squared plus y squared. Okay, so to do this, you're going to have a two-dimensional convolution, so you need 2 integrals. Okay. And then you can already write like d xi, d eta, or something like that, right? By using two 1D convolution integrals, calculate the 2D convolution. Oh, okay. So actually, they don't want us to do that. Let's see, what do they want us to do?
Introduce the eta as a shift on 1.
Yeah, so let me, if I get this wrong, I'll send out a correction, but let me just do this right. So we basically want, you're going to have one of them, which is going to be like an x. So this is, you want something that has f of like x minus I, y minus eta, right? That's one of your terms. And then the other term can be, stay as h of xi and eta. Okay? So then you just plug that into your formula. You have f of x minus xi, y minus eta. So you replace this x with an x minus xi plus a y minus eta, right? And then you have a times exp minus xi squared plus eta squared. Okay, and I think the idea is then, because each of these only involves one variable, right? Then it should simplify fairly easily. And as a hint, you want to use equation. Let's see, what is it? I think it's equation. Equation 2.54 is going to become very handy. Okay. Because one of these is going to be an integral of like a, so use equation 2.54. somewhere the derivation is a few lines, and then somewhere in the derivation is going to be useful to use equation 2.54. So that's one hint. The other hint is what is the integral of an odd function? Okay, so if I have an odd function, so first of all, what is an odd function? Like a sine wave. Okay, so what's the integral of a sine wave from minus infinity to like over any sort of symmetric interval? 0, right? So if I take a integral of any odd function over a symmetric interval, it's going to be 0. So that's another clue. Okay, what is integral of an odd function? Okay, so that should be enough to get you a problem with the homework 2. We're not going to do Fourier transform today, but let me just let's just look at the problem just sort of to say what you might want to think about as you're doing that problem. First of all, the scaling, I think for this one you're asked to do 2.6b, 16b, which is the scaling property. And so let's just go over that. All this means is that if I have, let's say I have rect of x, which is this function, and that gives me this Fourier transform sinc kx. Okay? Then let's say I have rect of 3x here. So that's just a squeezed version of my rect function. Okay? And it turns out if I apply the scaling theorem, it's just 1/3 sinc kx over 3. Okay? And so this is a stretched out version of my sinc function. So the basic idea that you want to keep in mind for the rest of the course is anytime you squeeze something in one domain, you get wider in the other domain. Okay? So it's basically the uncertainty principle. And then where that's useful is, I think Professor McVeigh's already talked about modulation transfer function. So in a point spread function, or in this case the LSF stands for line spread function, but they're basically the same. So these are basically your impulse responses. Okay? So the modulation transfer function, or just the transfer function, is just the Fourier transform of your point spread function. So you just take the Fourier transform. So you notice as these get wider, right, or actually let's say we start off, so this is a lot of blurring, right? Lots of blurring. And then this is less blurring, right? Okay? So you notice the Fourier transform. This has a very narrow width, and then as this gets narrower, this gets wider. Okay? And this gets to a little bit about the question we had before about, why do you accept some amount of blurring? So you see here we have to collect a lot more data in the Fourier domain to be able to get a very narrow impulse response. Here I can get away with a lot less data in the Fourier domain, but I end up with a wider impulse response. So that's the trade-off that we'll talk about when we get to MRI. All right. So with that, this is just if you use substitution of variables, right? It's basically a 1 or 2 line proof. Okay. So it should be fairly easy for most people to do. And you know what I mean by that, right? If I have an integral of something g of ax, then I define u equals ax and just, do the usual calculus 1 thing, right? And then the next problem that you guys had, and we'll go over this other stuff later. So here, sketching the impulse response function, you can sketch it by hand, you can use MATLAB, do whatever you want. And then what is a transfer function? Well, so you just take the Fourier transform of this guy, right? And so you're going to want to make use of the fact that the book has already given you, well, this is too slow. So the book has already given you one Fourier transform. So you want to take advantage of think about things like separability and scaling. Okay? So that's some things to think about there. And once again, if you do that, the problem is only 1 or 2 lines. Okay. So I think we've come to the end of the session. So are there any last questions that people have?
Is it okay if we use MATLAB to solve for this problem? Or do you want to do it?
I think I think it's fine to use MATLAB, but it may not be a bad idea to sketch it by hand because on a quiz, you want to just make sure you know how to do that. Yeah, anything else? Okay, great. So we'll post these. I'll post the video, and then we will have the next session in 2 weeks from now. Okay, thanks. Sure.